Okay, let me start the recording and get straight to class. Okay. Okay, so can see the screen, everybody?
Yes.
Yes.
All right. So we will move into our chapter 1, right? So what's with this entire chapter 1? Okay. So basically, it discusses the introduction to computer-aided design. All right. So your subject is computer-aided design. Okay. But here we will share with you the description of CAD, CAM, computer-aided manufacturing, as well as CAE, computer-aided engineering. Okay. Just a minute. Okay, I'll off my video just in case. Okay. So now moving on, right, to the objectives that is expected, right, out of this chapter. We want to here understand, sorry. Okay, so we want to here understand the various spheres of manufacturing activity, okay, where computers are used. Remember, our subject is CAD. Okay, so I'm using actually a desktop mouse, so you need to pardon me with the pointer, you know, the ink going wrong. All right. So we are actually wanting to understand the various spheres of manufacturing activity, and you would notice that this is the first objective. So we are talking about CAD, but our objective is understanding the spheres of manufacturing activity, okay, whereby computers are used. And then we want to understand what is meant by the product cycle, with the differences between the conventional and computer-based, again, manufacturing systems. And then definitions of various computer-based applications, CAD the application, types of manufacturing organization, it will just be a small intro, computer again, CAM and CIM. You see, 1 manufacturing, 2 manufacturing, all right, 3, 4, 5. Okay, so you would have heard the video. Okay, so you all would have heard the video that I actually had shared with you all. Can someone over here describe to me why in a CAD class we are talking about manufacturing at the beginning of it? Anybody?
Sorry.
Sorry?
Tak berapa dengar tadi.
Okay, why in a CAD class, right, are we speaking about manufacturing, you know, at the beginning of the slides? You see, let me try to close down the presenter view. Okay. So you see over here, we have so many manufacturing activities, right? So why are we speaking about manufacturing here? Kita sepatutnya we want to learn about CAD.
Because it is somehow related.
What is the relation?
Before we manufacture something, we have to design it using CAD.
Correct. Okay. Before we have to manufacture something, we need to design. Are you all hearing echo?
Yep.
Yes. Yes.
Yes. Okay. Right. I'll off the camera. I hope it's better. Okay. All right. So before manufacturing, we need to actually design something. So the entire concept of even beginning to design anything for that matter is to, in the end, manufacture. So generally, we don't embark into design activities because we want to hypothetically design. So saya rasa macam nak design something, I feel like, okay, I want to, you know, test the design here, test the design there. if you notice in the busy world that we are moving on today, whatever the field is, okay? So a design from the mechanical engineering point of view or engineering point of view, we are looking at tangible, you know, structures, items, you know, products and everything, right? So products could be all types. Like we have COVID-19 now, and we had to design the solutions for the COVID-19. So what are all the solutions for COVID-19? Can you all tell me that they have put forward so far?
Vaccine.
Vaccine.
Some more?
Wear mask.
Correct. Some more?
Social
Social
distancing.
distancing.
Okay, social distancing. Just a minute. Okay, so you all mentioned vaccine, mentioned mask, and mentioned social distancing. Okay, anything else? Which is a solution?
Test kit.
Test kits, right? Okay, so we have other things. We have, like, you know, some of them, you know, identifying medicines and many other things. But okay, out of the 4 at least that you've mentioned over here, 3 of it are products, all right? And 1 of it is a measure, a system, okay? So while we are designing, okay, so 3 out of 4 are products. So the very fact that we need to design that product. So when you use the term design, we will refer to building a model, building a, you know, something tangible. The vaccine is tangible, the mask is tangible. Of course, the mask, you know, face shields, all right? Like that, we have many things, right? So while the mask is something tangible, all right, it has a shape which you are going to model it, okay? Whereas the vaccine is something, it's not exactly a shape-based thing, you know, it is a fluid, but it goes by the concept of design because we are trying to, there was a need to build it, all right? And there are some formulations put forward in order to actually solve a problem. Okay, so that is the situation with a factor of designing, and why the vaccines, the mask, the face shields, the test kits all came about, all right? Because there was a need, and after the need, while we just don't hypothetically, you know, come up with the idea, we need to manufacture them, okay? So when it comes into the aspect of manufacturing, will be the time that you will realize a lot of problems come about. Like for instance, let's talk about mask. Now, why I'm using COVID-19, this particular semester, okay, we can imagine. So hypothetically, we can say, all right, we want a mask which can, you know, 100% foolproof the virus entry, or we want a mask that, you know, is comfortable. We want a mask which is breathable. We want a mask. So all these are what we call demands or needs or problems faced in the current society. Okay, so these are ideas put forward, and then we need to come up with the solutions, all right, based on your design. So I can just say, okay, a breathable mask. So we have to look at the materials, for instance, we have to look at the shape, and we can come up with all kinds of ideas. Now, all these ideas are fair and fine until they go into your manufacturing plant and they get stuck there because there are issues with the concepts you put forward. And once that is done, the next part that it may get stuck is once it is manufactured, the application may not be as intended. You know, there could be possible problems and all these things, all right? So if you notice, as we speak about...
Doctor?
Yes?
I don't see this slide. I just see the Microsoft Team.
Yes. I'm actually using that slide behind it.
Oh, okay.
All right. Thank you anyway. On and off, if you all see that, you know, my slides are not moving, suddenly my voice is gone, all these things, please take the trouble to highlight. Otherwise, I know I might just end up speaking not knowing that I'm out of the meeting. So, okay. So, right, having said that, okay, so there are issues which are going to be potentially happening in your manufacturing plant, okay? Another thing you would notice is you are all, I think, have been briefed about your mini project. So in the mini project, okay, you are expected to come up with a product or redesign a particular product, okay? and go about its you have to critically analyze the product, why the product came into being, what was the design evolution of the product, all right, what is the need for that product, is there a significance for that product in the market. Once you go through all these phases, all right, then you will come into the designing of the product. Okay, so while all this is happening, a few semesters back, especially during the face-to-face times when we had classes, there were times where we request students to actually design a product, but then we expect them to innovate a product. So when we talk about innovating a product, then the students will like I can just throw this topic to all of you for the mini project. Okay, let's work on a let's just say a novel mask for COVID-19. All right, so come up with all your innovative ideas, and we will have all the multiple groups coming up with different ideas. While the ideas can be just blasted forward, the issue is, can you manufacture them? All right, or can you apply them? So we want to know whether it's manufacturable. Next, is it applicable? Is it usable? Okay, so the whole idea of coming up with design just to throw it as an idea is very infantile. It's very childish actually. So it can only and will only be taken seriously when you start looking at the manufacturing aspect of it. So hence, what's going to happen in your mini project? When I say innovate a mask, we will have like all kinds of ideas. But the thing here is most students will just get away with it. Okay, only when it's brought down to manufacturing, you will realize, aduh, idea saya ni tak boleh jalan. Okay, this is not working, that is not working. So that is the point why we want to understand the issues behind the spheres of manufacturing. Okay, so the link between the design and the manufacturing, okay, is obviously we design something, all right, to manufacture it generally. Next, in order to manufacture something, you must have a design. Otherwise, we cannot manufacture out of thin air. So that is the direct, what we say, obvious link. Other than that, why do we need to understand what's happening in the manufacturing? Because every mistake or error that you do in your design is going to impact manufacturing. It's going to impact production, and it's going to finally impact the application. Okay. Are you all clear so far?
Clear, Doctor.
Yes.
All right. Okay.
Okay.
So now we come into the computer-aided environment where we understand computers, all the more you would have understood in the entire pandemic, they've become very crucial to our daily life. Okay, this was a slide made easily, like this particular page of the slide was made like 5-6 years back. Okay, where it was crucial, and now all the more crucial. Okay, so without computers, I think almost everything will crumble in general at the moment. Okay. So when it comes to the entire manufacturing aspect of it, right, in engineering practice alone, right, computers are used in all these areas, okay, and specifically we will use computers, right, for design and manufacturing. So under design and manufacturing, we use computers for drafting, for design, simulation, analysis, and manufacturing. So design, analysis, and manufacturing, they auto-explain themselves. You can look at the slides, the previous recordings, all right, to get the in-depth understanding. The difference between simulation and analysis. Analysis, we want to actually diagnose errors in your model or your product which you're designing. And simulation is such that we want to identify how the product moves or behaves in a kinematic situation, all right? If you have a product with, mobile joints, right? Where there is a motion of mechanism, right, in place. So at that time, we can actually simulate the movement, okay? So analysis is to troubleshoot the situation. In simulation, you troubleshoot as well, but it's more of the kinematic movement of the product. So basically, computers are classified into two areas in the manufacturing. Okay, again, term manufacturing. The first one is to monitor and control the manufacturing process, okay? And the second one is the manufacturing environment itself. That means in the production plant, what is happening. So this is the actual manufacturing. This is the part you would understand as manufacturing. Now, to monitor the manufacturing process is actually the design, okay, coming up with a part. So design comes under this section, okay. So these are all the different terminologies which we actually, have in under computer-aided processes. So I encourage you all to go through the previous videos to just have a look at it, right? CAD, what is CADB, all right? CAPP and all those things. The different terminologies. So what is important here is you understand all these abbreviations, they stand for something. Okay, so the major areas under CAD and CAM, all right, is geometric modeling, where you model your product, design it. Then we have computer graphics, okay. Without computer graphics, for all of you who play games, you know that your game is not going to be working, especially the current games, if you don't have computer graphics, all right. Why do you need computer graphics for games? Anybody? Can somebody tell me why do you need computer graphics for games?
So that we can play the game smoothly.
Smoothly, all right. Without the computer graphics, when you mean it's not smooth, what exactly are you experiencing?
Lagging.
Anything
Frame
else?
rate. Frame rate.
Sorry?
Frame rate.
Okay, anything else?
Design in the game. Character.
The design in the game meaning?
So the graphic will looks nicer and smooth.
Okay, so hence, for those very same reasons, right, we need the computer graphics for our modeling in our softwares. So you all would have been exposed to SolidWorks, some of you, before this, all right, or even those from Matrix Katia. Hence, you will understand when it lacks the computer graphics, it will not be smooth. Okay, so we have the geometric modeling, we have the computer graphics, and then we have the design application. So the word application would indicate the softwares. So softwares means applications. So we have Katia, we have SolidWorks, we have Creo, we have PTC, all these kind of things, okay? And we have manufacturing applications. That means manufacturing softwares like Mastercam, Moldflow, CAD, Mold, like that, okay? Different types. Okay, let me just actually, share a video with you over here.
Technologies allow
So just hear this out for now.
What is CAD, CAM, and CAE? CAD, Computer Aided Design. It deals with the 3D modeling. CAD design integrated with computer technology and engineering design. CAD, which through design can design anything like real-time with accuracy. In CAD softwares, both 2D and 3D dimension can be designed.
So this is the situation here. We integrate the computer technology, right, to design from the engineering perspectives. Of course, we can design anything. For instance, like we have, as I said, in the pandemic, even vaccines, right? We have the mRNA vaccines, which are primarily coded, and it is a simulation. So we actually code RNAs through computer technologies. So here we are talking about engineering design, but it could mean anything that you're actually trying to build upon. Moving forward, we are moving into a lot of artificial intelligence. Therefore, the usage of computer into designing anything for that matter there's a huge potential for it. And you can design anything like a real-time situation, okay? So this is moving forward. We can actually build, any kind of images exactly in a real-time concept. Right now, you're not exactly doing it in the full, when we talk about virtual reality and everything, that's more real-time, augmented reality and all those stuff, right? But over here, at the moment, we are looking at when we are designing something, we can re-simulate something which looks absolutely real, right, through the software. And we can do 2D and 3D designs.
Usage and advantages of CAD softwares. CAD software allows designers to work faster and smarter. CAD softwares allows design teams to control the quality of the final engineered product. The measurements, angles, and dimensions of a product are all conveniently recorded and saved for future use. Now see, what are the major CAD software available in market? Basic software for both 2D and 3D in CAD is AutoCAD. It's developed by Autodesk. Next one is SolidWorks. Developed by Dassault System. Main thing in SolidWorks is user-friendly and easy to learn. Next one is CATIA. Developed by Dassault System. It's mainly used for surface modeling. Another one is Creo. Developed by PTC. It's replacement of Pro E software. Final one is NXCAD. It's developed by Siemens. Next one, CAE, Computer Aided Engineering. It deals with analyze the 3D model.
No one likes being.
CAE is computer software to simulate the performance in order to improve product designs. CAE also consider simulation, validation and optimization of products and manufacturing tools. What are the areas covered in CAE? Stress and optimization of products and
So these are functions of CAE, all right? You can simulate performance to improve design, okay? Early on, you would have seen there was the car crash image, and now this is actually the manufacturing image. And you can simulate, you can, once you find out the problems in your simulation, you can optimize. And once you actually find out the issues, right, you can validate back with real-time data, experimental data to ensure that what you are proposing as a CAD model, right, is absolutely equal to the real model, and hence we can move with all the further and future diagnostics or what we call predictive possibilities with the CAD model alone, and hence we move into the design. So the aerospace industry heavily relies on this, aerospace, automotive industry.
manufacturing tools. What are the areas covered in CAE? Stress analysis on components and assemblies using finite element analysis FEA, thermal with fluid flow analysis, computational fluid dynamics CFD, analysis tools for process simulation for operations such as casting, molding,
Going in my way, but it's not like I need it. And you may have some history.
and die press.
You made this.
What are the software available in CAE? First one is ANSYS. It's analyzing strength, toughness, elasticity, temperature distribution, electromagnetism, fluid flow, and other attributes. Next one is HyperMesh. It's capable of producing meshes that are high quality, made with no complexity. Next one is SolidWorks, developed by Dassault System. Finally, CAM, Computer Aided Manufacturing. CAM is an application technology that uses computer software and machinery to automate manufacturing processes. CAM software is used to design and manufacture prototypes, finished products and production runs. Software that tells a machine how to make a product by generating tool paths.
So this is one of the major functions of CAM, right? The softwares will actually build the codes. We call it the numerical codes, okay? CNC codes or NC codes, computer numerical codes, to generate what we call the tool path to build the manufacturing parts, okay? So it is auto-generated based on your design, and it just auto-links, and we can sit over there like, you know, someone who doesn't know anything and let all this run. Okay, about someone who doesn't know anything, of course, you need to know how to use the software, you need to know how to link and everything. But, you know, like I can share with you during my uni days, okay, we didn't have, although CAD was already present, there was no automatic linkage to the machining softwares, machining machines itself. So hence, just a minute. So there was no link to the machines. So hence what we needed to do was actually manually, you can see over here, key in all these individual codes. So if I don't know how to do this, it was an absolute headache because it meant that I need to learn all these things out. But now, once you are in the software, it will auto-generate and it runs, okay, based on your design alone.
Now see, what are the few softwares available in CAM. First one is Master CAM. It allows for quicker modifications to making the part on the CNC machine. Next one is Fusion 360. It's developed by Autodesk. It's working simultaneously 5-axis for manufacturing process. And final one is NX CAM. It's developed by Siemens.
Okay. So this is a brief introduction, all right, animated introduction to CAD, CAM, and CEE. And this video over here, okay, I will upload this notes, re-upload this into UFuture because these links were not present. Yeah, let me just see if this is another.
New Librest liners. Now with new and improved curve fit technology, plus zero crumpling. So it fits and stays in place all day. Get one today.
You would notice this word, important industrial art, okay? So art was never exactly linked to science, okay, or engineering to begin with, okay? But here, the term art is included because if you notice, almost everything that we design, we require a perspective of beauty to it, perspective of aesthetics to it, right? So in every design that we make, while we expect the functionality and the performance to be intact, right? Wherever we can fit in beautiful features, it is actually recommended. And CAD as a tool allows us to actually what we call navigate, right? The design in such a way that it creates beauty, like a curved, sleek car. So in the automotive, you can see how your cars look today, right? Ships, aerospace, and every other usage. Okay, so the other video I'll let you all go through yourself, all right? Okay, now we come to computer-aided environment in manufacturing. So this slide actually gives us what we call like an overview, all right, on how an industrial plant will actually look like, okay, in a production plant where products are being made. So we are not looking at services, we are looking at direct tangible products being built and designed, okay. So in such plants, they actually use computer integrated manufacturing technology, okay, CIM. And this simply means that we integrate all the working systems of the plant together with manufacturing concepts, all right, to enhance the productability, right, and the performance of the product, and to enhance the efficiency of the plant in a general, okay, the manufacturing plant. So for a computer integrated manufacturing technology to function efficiently, we need computer networks, we need system designs and analysis, and we need to be having a system where we have process distribution, database management, expert systems, quality engineering. All this must be present for a full successful CIM technology. So in a plant, right, or an organization, right, which is actually manufacturing a product, for instance, let's just take cars, all right, you will have a system where you have your design center, okay, and you have your manufacturing center, and your manufacturing and design, actually it's linked to your manufacturing production floor. So this is the production floor, and all these things are controlled by a financial capacity, okay, financial system. So where your design is what you standardly will do. You come up with the design of the car with the aid of all these features, all right, and then you will test the manufacturability of that design that you propose through your different manufacturing softwares, CAM and everything, and then you send them for production. And under the production floor, you have all these things: production control, material resource planning, quality planning, and everything. And all these things obviously must be controlled by a business system, all right, where your financial capacity is actually moderated or monitored, okay. So both moderation and monitoring will be done from obviously the exact financial point of view, and this is, you know, all the staff, vendors, and all those kind of things. And this is actually the financial point of view for your products. That means to make that product, I need material, right, and directly I need the resources for my manufacturing plant, like electricity, all the utilities and all those things will fall under here. So this is an overview of how an organization would look like. So coming into the concept of design. So what exactly is design? So it's an activity, right? And the activity needs to be extremely well organized, and it must take into account all the influencing factors, right, which are going to be responsible for the success of the product. So when we talk about all kinds of influencing factors, you must see, and that's when you will look at the manufacturing point of view. Wait, just a minute. Just a minute. All right. So when you look at the manufacturing aspect of it, then you will understand, all right, how and what factors will actually influence your product. And the complexity of your design itself, it's linked to the design process, okay? So the more parts you design, naturally, the more complex it becomes, okay? So while just now we described design, here we're describing CAD. So what is CAD? Well, design is just generally an activity. CAD is a, you know, computer-based design activity. Therefore, it needs the use of IT, okay? Whereby under the IT, we have the hardware, we have the software, and we have, the software, and we have the external peripherals. So the hardware, okay, so you have your hardware, your desktop, you know, your CPU system, and then your software, like we were going to use CATIA. And then when we talk about peripherals, it'd be like, you know, your extra peripherals, like your mouse, your printers, and all those kind of things which enhance your design function, okay? So the core of a CAD system is naturally the software. You don't have a software, you don't have an application, you cannot actually claim that you have a CAD system, okay? So I'm not going to go through this because the slides just now showed you, right? CAD allows you to accurately design something and easily modify what you're designing. So under product engineering, under design, these are all some of the terms which are used. Okay, so I encourage you all to go through the recording of the previous video to actually understand these different terms. Okay. Okay, here I will take some time to describe this. Okay, so now we come to something called the design process stage. So early on at the beginning of the class, I asked you, right? Why is there a link to manufacturing and design? And you told me because in order to manufacture something, we need to design. But why do we even design anything? Because, like we used the COVID-19 example, there was a problem. A problem occurred. What was the problem? There was an illness that came about. So we need to find a solution for that. So like that, a problem is usually identified. And once you identify the problem, the next is to understand whether is there a need to actually solve that problem or not. Okay. So if you, let's just say that you have an illness in the environment, but you know, we have out of 7 billion population in the world, the illness is only killing, let's say 10 people, right? On and off for the next 5 months, all you noticed was 10 deaths and maybe a few hundred infection. Okay, so it was a problem. Okay, no doubt it was a problem. But does it have the need to come up with what we call massive solution? Then we have to think about it. All right. So like that, let's just say you want to design a car. So is it, okay, not design, if you want to optimize certain functions in the car, for instance, there is a problem, like we get stuck in jams, we want to have, you know, let's say, hybrid fuel system, all this kind of things is to, you know, help the environment, helping the cost and all this kind of stuff. So these are all needs which we need to answer, okay? So we need to recognize whether is there a worthiness to actually coming up with that solution. So the first step in design is identifying the problem and next to see whether there is a need to actually solve that problem or not. So based on that, some questions will be asked. Who is having the problem? What is the problem? And why do you need to solve that problem? Okay. So these are the questions which need to be answered before we embark into the next level. So when you answer this, you can justify, then you move on, okay, into defining the problem. So we say there is a problem. So what exactly is the problem? All right. So you need to put it out point by point by point. And each of this problem, there should be a concept of solution. So there should be a conceptualized solution for each of this problem, all right? So if you say that, no, I'm getting, you know, with this, the current petrol fuel, right? It is not very, you know, it's not going to be very much appreciated in the future because we are running up soon. It is going to be a situation we are going to be running out of fuel, right? It is not, it's not a renewable energy. Okay, so hence we want to look at, and it has an impact on the environment. Okay, so these are all problem definitions. Therefore, we need to come up with a conceptual solution to the fuel alternative. So we have, you know, electric cars, hybrid cars, all these different functions which actually injects a concept to solve the problem. So as you put out your problem definition, you will come up with a concept to solve that problem. Once that is done, then, okay, you embark into geometric modeling. Okay, so over here, when you're discussing all these things, it will lead you into actually coming up with the intention for design and the objectives. Once the objectives are there, you need to actually also state the constraints or special criteria. So not everything you suggest can be done. So there will be a limitation. So those things have to be listed out. And then we go into geometric modeling. Okay, then you come into the reality of your model. Okay, whatever that you're speaking about over here, you can bring into reality. Okay, and whereby you will actually build your model virtually. Okay, and once building, we specify the parametric, you know, the parameters of your model, the dimensions, and any other parameters, okay, involving it, and we draft it. That means we have the drawing so that it can be understood by other people. So moving forward with your geometric modeling and spatial analysis, of course, we're talking about the term spatial analysis here. In your model, there should be what we call, when there is an assembly system, there should be proper spacing between two parts, all right, especially when it involves a kinematic joint. There should be no tight fit, there should be no loose fit, there should be no interference, clashes, all those things. Okay. Once we come up with the model, then we analyze the model. So this is here, this is where CAE comes in. So why do we analyze the model? Okay, because we want to justify that the model that we're doing is correct, and we want to ensure that the model that we are building is not going to face any potential problems when you manufacture it. So for all these reasons, we diagnose problems in the model. And if there are any problems, we optimize, we correct it. Okay. Only then we go into developing the prototype. So prototypes are developed for multiple reasons. One is to show the display of the model. Next is we want to actually experimentally validate the model. Only then we go into developing the manufacturing process. So here we do the CAM. Okay. So CAM is done under the CAE part, and CAM is also done under the manufacturing development. So the CAE part of it is here. We analyze the manufacturability process through CAM. Next is we generate the manufacturing codes through CAM. Then only we implement manufacturing. So this entire thing, the story over here, speaks about the design process only. Only when it moves into the production plant, then only the actual manufacturing activity begins. So I'm not going to go through the advantages of CAD. It is very, very direct. You all can read through directly. Okay, faster, easy. You can edit. You don't need to repeat. Okay. So earlier on, you saw in the video what was the description of CAM. Okay. So CAM can be manufacturing itself can be done in 3 batches. Okay, mass, batch, and job shop. So this is mass productions, usually more than 10,000 parts. Batch is about 100 to 10,000, and job shop is actually custom made, all right, products, which is about usually 100 or less in quantity. So these are all the terminologies under the manufacturing engineering, which you can look through in the previous recording. The advantages of it, all right. So you see the advantages of CAM. The first one, we have more design freedom because of CAM, and because we can identify what can go wrong in manufacturing, you have a greater design freedom, and all the other things which are, you know, increased productivity and everything sort of stuff. So these are some CAM techniques. Actually, the third link earlier on, which I had, okay, which has a video, it actually shows you some of the CAM techniques. Okay, in your CAM software, these are a few things which you can study, like turning, EDM, and many other things. And then we have the CAE, okay, which I mentioned earlier. It's to diagnose problems, isn't it? All right, and optimize and validate your part. So these are the areas under CAE where you have stress analysis, fluid flow analysis you saw earlier. You can actually visualize your kinematics. I told you study the motion, all right, of mechanism in your part. Okay, and then so all these things we saw in the video just now. These are all the advantages. Basically, what CAE does, it shortens your manufacturing time and cost. Because of CAE, we can forecast all possible errors that's going to come out, that when you embark into manufacturing, the first run is the correct run. Okay, so that's the concept of it. Okay. After this slide is actually the intro to the chapter. The next slide onwards is actually a summary of different chapters being just inserted in. So I'll run through this very quickly. Okay. The point, they are all like, you know, summaries of chapter 2, 3, 4, 5, because this is an intro chapter, right? So I'm just going to actually just skim through, so you can also look at the previous recording, okay, later on. So this is an example of an assembly drawing, a very detailed drawing, okay, for a manufacturing product which is going to be manufactured. So you can see all the manufacturing indicators, all right, your bill of material, and I'm going to take a full description. Okay. Now, engineering activities, okay, the slide, all right. engineering activities are in general, okay, divided into 3D modeling and documentation, manufacturing engineering, functional design, which is linked to 3D modeling. Okay, when you're modeling something, we want to ensure that your design is functional. Takkan we want to model something where your design is not functional. Like I told you all, if you model a mask and you come up with all kinds of cool ideas, but actually it's not functional, so it doesn't make sense. And then we have analysis and we have others. So what comes under others, right? You see under manufacturing and engineering, under packaging, distribution, marketing, all right, plant simulation, okay, they all come under the other activity. After sales service, okay, so they all come under the other activity. Now, if you look at this chart over here, 3D modeling, documentation, and functional design, you notice takes up a larger amount of involvement compared to manufacturing engineering. So can you all tell me why? Why this two takes a greater involvement? Even as a single activity itself, the involvement is larger, all right? Now, combine this as an activity also, the involvement is certainly larger than all other activities in a product design. So can you give me any reason why you think that that's the case?
Make sure the product function well.
So that the product functions well, but for ODL tester, the kind of questions that I'm asking you all in the online class are going to be possibly the type of questions that will come up in your test, because it's going to be questions where you cannot get your answers directly from the notes or the internet, so you have to actually come up with reasonings. All right, so here my question was, why 3D modeling and documentation and functional design has a larger involvement in percentage or time or whatever function of activity compared to the others? So the answer given was so that it functions well. But let's say it's a 3 marks answer, so you will not get your full marks. So how else you will describe it? So I need you all to speak. Anyone? Are you all there?
Here.
Okay,
Yes, Doctor.
okay, come up with any. It's not like a one right or wrong answer, Anybody?
The product itself. So I can see the picture.
Okay, it's the chart.
Maybe the 3D modeling and documentation and functional design is related to the product itself.
Related
So
to itself.
so that it involves more on the product design activities.
Okay, but why is it taking so long? The timing or the percentage of involvement?
Because it
I think
requires
because when you want to design, a part, you have to consider to build another smaller part. So yeah, I mean one part but need another small few part to be built as a component, I think.
Any other answers? Okay, thank you for those answers. Anyone else?
So that we can know the limitation or the error that might come up from the product when we design.
Okay, all right. Anyone else?
maybe it require the test to determine whether it's complete the objective. I mean to solve the problem that we have to solve using the product.
Okay, So the last two answers, right, to identify, what it's needed to actually, solve the problem, right, to understand the product, and then to test the product itself. Okay, they are pretty much close answers, right, representing. So the way is you need to express yourself as well as you can. So the whole idea of why this much of time is taken over here, if you go back to this. So that's the slide, and this slide is actually linked, right? The entire design process stage, you see all these functions. All these functions fall under this, and this. Sorry, 1, 2, and 3. So when you talk about manufacturing engineering, this is the production floor. Okay, this is the production floor, and this is the after-sales service. Or marketing, going towards sales. All right, but everything else comes under the earlier part of design. So the amount of things you need to do over here, to brainstorm and understand if you have a problem, to come up with a concept and ensure that the concept is workable. Imagine you want to build a flying car. You definitely know a flying car is going to solve a problem even now, if we have one, right? We won't be stuck in jams and everything. But why can't we embark onto it? Why we can't embark onto it is because we cannot define all the possible problems, and we cannot come up with a concept so quickly as to ensure that it is feasible and it's workable. So that is how long it takes to actually get a problem solved and moving it into ensure that the design is functional, and then building the geometry. Then only we analyze. So building the geometry, making sure the concept of a flying car works. It's not like nothing has ever flown before. We have airplanes flying, so we have helicopters flying, so we can adapt what we say, adaptive design. We can actually adapt the concept, but it's just not as simple as that. So all the issues that you need to take into consideration fall under these two sections. So when you answer questions like this in the test, always slot in with an example so that you can speak about the example and explain better. Okay, so a lot of issues need to be hammered out over here. So what you can do is you can give an example and then explain based on an example what are the things that you need to solve over here, solve over here, solve over here. Hence why it's taking so long. Okay, so that's the whole idea over here, to finally ensure that your product is functional, it's feasible, it is workable, and it will actually solve the problem which you have identified. It's not as easy as just drawing a box, designing it, and manufacturing it. Okay, it takes much more than that. Okay, so this is for the engineering activity. So you may get questions, things like what are all the functions, what are all the activities under the other category, what are the activities under manufacturing engineering category. So these are factors you need to actually understand and explore. Okay, these are the use of computer graphics. Okay, you can just run through the slide. In mechanical design, these are all the different designs you can do. Architectural design, all right. So CAD can be used under mechanical engineering, under architectural engineering, where your software will have different tools to formulate this kind of designs. Electronic engineering, where you have different tools like this. All right, so this is actually a precursor to your chapter 3, okay, which speaks about chapter 3 or chapter 4, sorry, where it will speak about geometric modeling. Okay, so geometric modeling in chapter 4 will tell you how the design evolves from wireframe to surface to finally solid modeling. So we started off with 2D drafting tools, okay, in our earlier days where CAD was first started, all right, AutoCAD was the first software, and it was to actually replace traditional design on drawing board, okay. And it was good enough because imagine all those drawings, the massive drawings which used to be on papers, right, went on computers. So it was easier. But it was not actually finally giving the CAD's advantage. So they moved on into wireframe design, where now you can actually visualize the part clearly, okay, and nicely. But it was not able to give you mechanical properties of the design. Hence, from drafting, it moved into wireframe first. Okay, so wireframe, from 2D drafting into wireframe, you actually get to visualize the part, but that's about it. Okay, you can actually visualize. You can't actually understand the properties of the object. You can't even identify the faces in between, which is in, which is out, like this. You don't know which is in, whether this was from which side, right? It just gives you a sketch outlook. And it's incomplete. You cannot get volume information. So a step further was to evolve into surface modeling, whereby you now get to see what is the outside and the inside of the part clearly, all right? And some analysis can be done based on surface modeling itself. But yet, what we cannot do is we cannot actually still get volume properties, mechanical properties of the object. So to solve that problem, we moved on into solid modeling, 3D solid modeling. So this is the final stage we are in now, where we can fully model the solid and understand every complexities of the solid model. So the modeling usually uses primitives and extruded body. All this will be discussed in detail in chapter 4. Okay, where you have Boolean operations, constructive solid geometry, CSG, and then you have boundary representation. So all these things will be there. Okay. So this is like Boolean operation. As I said, this will be discussed in chapter 4 in detail. All right. So, and then here comes CAM, all right, which was already discussed earlier on. Basically, the whole purpose of CAM is actually to integrate CAD and CAM and bridge, that means connect, all right, between both. And in the engineering, we are actually using it in order to identify the problem. So this is going to be, all this is going to be taught in chapter 6, all right. So this gives you just an overview of what FEA is. When you have a particular model, the concept of finite element analysis, all right, which is one of the methods which we are going to take, is such that you break the large part into small, finite, or we could say countable number of parts. So parts doesn't mean you break them into portions. Basically, you divide them into sections, all right? And these sections are what we call, like, you know, it's called the meshing or the elements, all right? And you will analyze these parts. That means you put the loads and the boundary condition on these parts based on each of these sections. So these sections are needed because mathematical formulations will be imposed on these sections. Once it is done, you'll be able to, like, if you have a load on this structure, all right, and which is constrained at the base, this is what's going to happen. It's going to deflect in this manner. Okay, a load on top, and this area and this area is fixed, then it will deflect in this manner. So you'll learn this in chapter 6, right? So basically we've seen, okay, how integrating CAE, what happens, all right? You reduce cost, you reduce your lead time, the production time, and you can reuse your model again and again. Right? And you can custom make your improvements necessary. Okay, now moving on into an engineering approach. We have two types of approach in engineering in modeling or designing a product or part. Okay, the first one is the sequential approach, and the second one is the concurrent approach. So what is a sequential approach? A sequential approach simply means that when you're going to manufacture something, it will move from one phase to another phase of your step of design or manufacturing. So you have design, you know, to analysis, to prototype. Okay, so this is a sequential approach. So only when you complete design, you can analyze. After you analyze, then only you make prototype, and then it's a step by step. So it's a slow process. People in the process planning must wait for the designer to finish. People in the manufacturing will not know what happens until the analysis is over. So it's a step-by-step process. So this was the initial process. Now in a concurrent process, everyone involved in the design has access to the data of the product evolvement or development. One go. Here it's one after another, here it's one go. So if you're making a car, right, it means the marketing person already knows what car you're going to make, how to market it. The quality control person knows what kind of quality control measures that you need to actually take for that car so that you ensure everything goes well and fine. The financial person knows what is the costing that is needed for that development and manufacturing of the car. the contractors, vendors, and everybody know what kind of tools, products, parts, assistance that they need to give in order to ensure that that particular car is successful. The customers, the buyers, all right, they know what car is going to come out. So you can see, right, cars in the market, it will be marketed first, the customers will find out first, while the development, not exactly development, but the manufacturing will be ongoing. Okay, in some cases, even development, a concept of a futuristic car has been already given to you, right? We have our self-driving cars, right? Automated cars, autonomous driving and everything. So these are concepts. It's not widespread in the market yet, and it's still in the stages of development. But as a customer, we already know what to look forward, okay, for the future. And design is ongoing, so everything is concurrently means simultaneously going on, right? So this is actually the successful approach for the product to be developed and marketed. So it's like, you know, you entice the customers with what's going to come out, that when it finally does, it creates a very big impact in the market. And everyone is also aware of what's happening. So we have all what we call the expertise from different areas. They can channel their ideas in to probably, you know, cross-check or troubleshoot the situation. So this is a concurrent process where this slide just tells us, right, in a business model, what are the inputs, processes, and outputs. So the inputs are, of course, we first need a problem. So that's the societal concerns and demands. And then, of course, we need all our utilities, energy, materials, software skills, and everything. And then in the process, we need to make the process run through the design, plan, production, and stuff like that. And in the output, what happens is you need to market it. And after marketing, you need your after sales service. Okay. So this is the linear engineering, where in a problem, linear or sequential engineering. If there is a problem, you need to always, you know, backtrack one step or two steps. Okay. Unlike the concurrent situation, where when your 3D model is being modeled, anybody can join into troubleshoot. So you see, it's a complete crisscross of information. The manager knows what's happening in finance. The production person knows what's happening in marketing, right? So this is a scenario where even the technician will meet the CEO. That's not the case in the sequential process. So in a concurrent process, everyone is aware of the evolution of the product. So this is actually basically what the term we call model-centered engineering design, where it's centered, right? The model is centered over here. And the idea, refinement, and implementation is centered towards the model. So whatever ideas that you have, whatever modeling, you know, improvements that you have, all right? And the implementation that you're going to make must all be centered around the model or the product to ensure it is successful. So any of these things, if it makes the product become a failure, then it's not going to work. So you keep looking at, you're going to actually model, let's say, a Honda Accord, you need to keep looking at the Honda Accord all the time. Looking at the Honda Accord from the design perspective, from the marketing perspective, from the production perspective, from the financial perspective, from the customer's perspective, like that. Okay. So basically, it's the sharing of your 3D CAD database, all right, which supports creative design process and production. And the separation in this process is actually no longer necessary. So it's a non-linear team approach, and it gives you all this higher quality product, satisfied customers, less manufacturing problems, and a shorter lead time. Okay. So that settles the chapter 1. Do I have any questions from you all?
No.
Anyone else?
No, doctor.
No, madam.
Okay, so if everyone has started, this class is recorded, so now I'll stop the recording.